We are now looking at a second traversal type problem. In this problem, we're given a graph, and the goal is to visit every vertex exactly once. This is called the Hamiltonian graph problem, or Hamilton path problem. So consider the following problem. We have a postman, and the postman has to deliver mail to some houses. In the graph you see on the screen, I've labeled this with a few streets, and I've marked out the addresses of the houses. For example, 49 on 4th Avenue is up in the upper left. So our postman needs to deliver to all the houses that are labeled in green and doesn't want to waste time by walking past the same house twice. So can this be done? Well, let's give it a try. I'll pick a place to start. Let's say I start at number 49. I can go across. So my postman has managed to go to every address and not repeat it. Well, let's change the question around a bit. What if I add a house on Boulevard A? So we'll put that in here. I won't worry about writing the address. And let's try again. Well, the same path actually works. So our postman can still deliver everywhere. Doing pretty good so far. What if we add another house, but on Boulevard B? Well, this is where we start to run into trouble, because in the past route we took, the postman ends in the lower left corner and has no way to get back to that missing house. Now, as we have seen before with Euler paths, a failed attempt does not mean it can't be done. So let's try again. Maybe I'll start at one of these houses that were added. It almost worked, but I've got stuck. I'm going to have to pass that house on Boulevard B again. So you can keep on trying on this, but I'm pretty sure that you're going to find that you cannot do this. So let's turn this into a general graph problem. Instead of looking at our postman, we're looking at any graph. And the question we were asking here was, is it possible to walk along this graph and visit every vertex exactly once? So this will be called the Hamilton path problem. If our postman has even better luck, he might be able to pick a place to park. Maybe he parks in front of number 49, does his postal route, and comes right back to where he started without repeating anything. So that's an even better question. Is there a path which visits every point exactly once and comes back to where it started? And that will be called the Hamilton circuit problem. If a graph has a Hamilton circuit, it will be called a Hamilton graph. Now, just to give you a warning, there are theorems that sometimes can tell you if there's a Hamilton path or Hamilton circuit. In a class where you're expected to learn definitions, usually we don't want you to use theorems like that. The goal is to find out, do you understand what this method is? So let's give this a try. And again, we are not going to refer to theorems from somewhere. And I'll comment later, but it turns out there is actually no theorem which gives you an easy way to always know the right answer. There are theorems which might help you once in a while. It'll say, well, in this case, you can do a Hamilton path or you can't. There's no theorem that quickly answers the question in general. This is a complexity theory problem. We'll look at it later. So let's start with graph number 1 on the left here. Can I visit every vertex exactly once? Well, I could start in the upper left, walk around, and come right back. Or if I don't need to come back, I can just end at the lower left. So thinking back to our definitions before, the Hamilton path problem said you visit every vertex exactly once. And we did that. So yes, Hamilton path. And usually you should tell the path. So if the graph does not have vertices labeled, then label them. One example of a Hamilton path here is A, B, D, C. And then it also is, well, we had a second term, Hamilton graph or Hamiltonian circuit. So yes, it is a Hamilton graph. And to do that, you would just follow this up by going back to where you started. I have given the Hamiltonian circuit. How about number 2? Well, let me give this one try. How about I start on the left? Okay, I've run into a problem already. I visited all those vertices, but I have no way to get to the nose. So first attempt failed. No Hamilton path, or maybe there is. Let's try again. Well, the nose made a problem, so how about starting at the nose? It worked. So just like before, I do need to have vertex labels. So I'll label those A, B, C, D, E, F, G, H. And the Hamilton path that we found was, well, I started at H, H, G, D, E, F, and I circled back around to A, B, and C. And that gave me a way of visiting every vertex exactly once. Now, what about Hamilton graph? So does this have a Hamilton cycle? Recall a Hamilton cycle must start and end at the same point. Well, the nose that caused a problem the first time is going to cause a problem again. Because if you start at H and wander off, you can never get back again without repeating G. If you don't start at H and you wander along, then once you go to H, you can't get away without repeating G. So this shows us that there is no Hamilton cycle. So no Hamilton cycle. And I just gave the explanation verbally. On an assignment, you might be expected to explain that in words. In that case, you would single in on that point H and point out that when you depart H, you have to go through G, and when you return to it, you have to go through G, and therefore you must repeat a vertex. Now let's look at the last example. I have indicated a green dot on there. This means the first time through, let's not have that dot there. So is there a Hamilton path? Yes, there was a Hamilton path. Again, with the green dot missing. Is there a Hamilton cycle? If there's a Hamilton cycle, I start and end at the same place. This is going to cause a problem because there's sort of a top block and a bottom block. And there's only one way to get between them. And so if I start on either the top or the bottom and cross to the other side, I must go through this point and I can't return through it without repeating. For example, if I do this approach, I can't get back again because I would have to repeat this vertex. So this shows us there is no Hamilton path, or there is a Hamilton path, but no Hamilton circuit. Again, on an assignment, you're expected to give an explanation. So you would follow a process like I just did, point out where there's trouble, and explain that in order to get from the top half to the bottom half, you must pass through that point. And to return back to the starting point, you would again repeat it. Now, what if I add in that green dot there? So at first glance, this is going to be helpful. We couldn't make the circuit because when I got to the bottom, I couldn't get up again. So let's see what happens. I'm going to set my standards low and just go for a Hamilton path the first time through. So maybe I'll start at the top. Okay, I've run into a problem because I can't get back to that green dot. Maybe I'll try starting at one of those middle points. Now I've run into a problem again because I have a whole street I can't get to. So something seems to be a problem here. So let's try to talk ourselves through it. If I start at the top, then to reach the bottom, I must cross through one of these points. Once I reach the bottom, in order to do both lines, I must loop around. For example, like this. But when I loop around, I have a problem. I get trapped on the bottom and I can't reach that other side. Now let's look at that green dot. So we'll try again to make a Hamilton path. We've tried a few options starting at the top or the bottom or the middle. So let me start at the top. I've run into a problem because I can't get back to the green dot. So maybe I should start in the middle. Again, I have a problem because now I can't reach that other street. So there doesn't seem to be a way to make this work. So how do we reason through it this time? Well, if you start at the top, you must cross to the bottom through one of those 2 points on the left or the right. Once you've done that, you have 2 roads to go on, and the only way to do both of them is to cross one and return on the other. But that makes you end back by the green dot, and you can't access that last missing point. What if we started at a middle point? In that case, once you pick a direction to go, then in order to cross both of those streets, you need to loop around. Well, now you're in trouble because you can't even get down to the bottom half. So this reasoning explains to us why we cannot find a Hamilton path on this graph. So we've seen one graph on the left, which has a Hamilton path and Hamilton circuit. We've seen one in the middle, which has a Hamilton path but no Hamilton circuit. On the right, it had both. Throw in one more house and our postman can't do the route without repeating, but originally he could. So if you imagine a real postal route with a lot more streets and a lot more houses, we could be fairly reasonable to expect that your postman will have to go by a few houses twice. Fortunately, they like to get exercise. Hopefully that's not going to be a problem for them.